Hess, analytics architect at DataStax. He spent more than 15 years in the big data space, starting with 10 years as a cryptologic mathematician in the U.S. Department of Defense. So he knows his data science, his data mining, and his large-scale data. And we also have Brian Dominguez, from the director at KPI Partners, who also in advanced analytics and business intelligence, and he'll share his story as well.
So this guy is a little bit of history. Willie Sutton was a bank robber in the 1930s, 40s, and actually into the 50s. And within the first month of being of the creation of the FBI Most Wanted list, Willie managed to get up on that list. And then he was actually captured a number of times, managed to escape a few times actually, and then was finally captured in 1952. The thing that's interesting about Willie is they asked him this question after his career of robbing banks, of why do you do that? Or why are you robbing the banks? And his answer was, that's where the money is. And so we're going to keep Willie in the back of our mind for a little while as we talk through some of these other pieces of the puzzle, and we'll come back to him towards the end. Now, talking about Cassandra and Spark and the whole space, I think that a motivating example sort of helps ground things. And so the case that I'll talk about primarily here is an Internet of Things use case. And, this picture's talking about connecting toasters up to the Internet. We've been talking about doing that for like 30 years, still never understood what the toasters would have to say. But nonetheless, it's the idea that we're going to have all these connected devices across the enterprise and out in the world connecting back to some location to deliver data. So we see this in a whole bunch of places. You get things like your thermostats, like Nest, and some of the others who are getting into that space. You see it with connected cars. We see it on manufacturing floors giving telemetry data for their data, smart metering, et cetera. And all of them, the idea is we've got our sensors, our devices out there on the internet, and they are sending data back to some central system. Now, that central system clearly can be distributed around the world, but from a logical standpoint, it's coming into this system. And now we have to think about what that system should do. So it needs to be able to receive from these various places, and it also needs to then be able to answer some relatively straightforward questions. Those could be questions like, what did that silver toaster say last? Or it could be something a little bit more fancy, like, what was the average number of pieces of toast per, toaster type, or something along those lines. Now, if we are at all successful in what we're doing, we're going to see more toasters coming on the scene. And our system is going to need to be able to handle the fact that we are successful here, and that the growth of the number of sensors that are out there is going to need to have our system's going to need to tolerate that growth. And then the other part is that we are certainly going to be in a world, the realistic world, where faults will happen. Nodes will go down because of hardware reasons or something. We had this situation almost a year ago where Amazon had to reboot a whole bunch of servers for some regular maintenance, and we hear about some, folks that were hosting things on Amazon, their systems became offline, while other folks like Netflix were rolling just fine. And we now talk about the Amazon outage and not the Netflix outage. So in that context of Internet of Things, we're going to talk about two things, Cassandra and Spark. And then we're going to talk about the two great tastes that taste great together sort of thing with bringing the two pieces together. So first, a bit on Apache Cassandra. So Apache Cassandra is a distributed NoSQL database. It is sort of the love child of the Big Table paper by Google and the Dynamo paper by Amazon. Big Table is really the data structure. So we're talking about tabular data with these sort of column families, and you're able to sort of have sparse storage of it. In other words, we don't store the nulls that don't happen for certain things. And it's a very flexible data structure. And then we've got the Dynamo paper was all about resilience and fault tolerance and having this concept of no master. That's an interesting element that comes into play with Cassandra that we make a lot of use of, is the fact that all the nodes are equal. And as a result, in that sort of democratized world, we don't need to worry about a couple of things. So first of all, there isn't a master to go down, and so we're always on. And if there's a node that happens to have a failure, say a network failure, and that node goes offline, the other nodes are able to pick up all the pieces for him. Similarly, since all nodes are the same, that means that all nodes are answering questions and queries to client applications, as well as serving up the data and owning some part of the data to answer those questions in the system. Means that if we double the number of nodes in the system, we really are not only doubling the amount of storage, but we're also doubling the number of questions that we can answer at the same time. So we usually talk in Cassandra, we usually talk about transactions. We merge the idea of reads and writes into sort of one bucket. There certainly are ways in which the read path and the write path are a little bit different, but we usually talk about transactions per second. So when we scale out, we can get more transactions and more data. One of the things baked into Cassandra, I won't talk too much about that on this talk, is really this multi-data center idea. And so we can have our data centers the data centers can either be geographically disparate because of either two things. One is fault tolerance, and so we can say that if there was a flood in say New York, like at Hurricane Sandy, then a data center there going out, the application can go to another data center, say on a high up on a mountaintop, far away from a floodplain. And so that's one reason. Another reason for geographic distribution could be the idea of wanting locality. So I'm going to do the guys in New York will talk to the New York server, and the guys in Los Angeles will talk to the Los Angeles server. But for this talk, we actually might be interested in the third reason for having this, and that's having workload isolation. And so those data centers can be virtual data centers. In other words, they could actually be in the same location, and we've just isolated them so that if you're doing a slightly different workload, you've got different hardware dedicated to it. And then last, a little bit on the Cassandra query language. Cassandra, when it first came out, was admittedly not the easiest thing to use. A lot of the easy use cases, very straightforward use cases, still required you to get down into the guts. Admittedly, the harder, more exotic ones also required you to get down in the guts, but you were probably willing to go that far with something that custom. And so we came up with this thing called the Cassandra query language, which looks a lot like SQL, but is a little bit deceiving. Basically, it covers all the operations that you would do in Cassandra in these normal sort of use cases, makes them very simple, and they look like the SQL analog. Now, that being said, there are things, and we'll talk about this a little later, but there are things that look like you should be able to do because isn't it an SQL database? But it is not, and that's part of where we'll come into Spark again in the story. So if we think just briefly on sort of how Cassandra works on writes, we've got our little Nest thermostat here. So Nest actually is using Cassandra, and he's going to connect to the cluster. Now, when he connects to the cluster, he actually sees the whole set of nodes here, and he can make intelligent decisions. There are all sorts of load balancing decisions that he can make. We'll do something simple. Let's say he's doing a round robin, and so he's going to share his workload among these 5 as he goes around. And so he's going to just tell one of them, hey, it's 72 degrees. And so that node may actually not own the data. And if he doesn't, that's okay. He's happy to be the coordinator, who we call the coordinator. I think of him more as like the maitre d'. And he says, I'll take care of you. I can route that question to who needs to know it or who needs to have that information. And so internally, he will pass that on to the node that owns the data. That person or that node will respond when he's done, and the coordinator or the maitre d' is able to reply back to the thermostat or to the client. So a few things going on there that we can actually start controlling here. And that comes under this large umbrella of tunable consistency. So consistency is one of the parts of ACID, but it's frequently one of the things that we take we don't really take advantage of in the SQL space, but we end up having to pay for. And so one of the things that's been done in Cassandra is relaxing consistency and allowing people to tune it to the needs that they have. And so by doing that, we're in a position where we can get different scale out characteristics, fault tolerance characteristics, et cetera. So the first thing to note is the data in Cassandra is replicated. You set that when you set up your table. And we kind of distribute it by token range. So each node is responsible for some portion of the range of tokens for rows. And so all rows have a primary key, which maps into that token, and based on the ranges, tells you where that data should be located. So if we keep it simple and we said that we had 100 tokens, we don't. We actually have a 2 to the 64 space. That number is a little too big to even for illustrative purposes. So let's say we had 100 token range. Then the node 1 might take tokens 1 to 20. Node 2 may take tokens 21 to 40, et cetera. Okay. Now, when we do writes, we have options as to how many of those replicas need to know the data was delivered before we tell the client that it's all done. And by combining reads and writes and these consistency levels, we're in a position to ensure some things about how the data is distributed. All right. And so this becomes a core part of the application and the design decisions that we make. And one of the things that's somewhat interesting about Cassandra. So the first one, the top upper left, is probably the most relaxed. Basically, what you tell the maitre d' is, hey, as long as you have it, even if you don't own it, as long as you know that you acknowledge that you've received this data, then you just tell me, the client, and I'll be happy. Now, what the coordinator is going to do in the background is he's going to make sure that, let's say we have a replication factor of 3, which is pretty common. The coordinator is always going to make sure that all 3 replicas get the data. It's just a matter of when he tells the client that things have been done, and you can some assurances around it. So the upper left is the most relaxed. Hey, just as long as the coordinator has it, it's fine. The lower left is just just make sure one of the replicas has it. Right? If one of the replicas has it, I know that it's durably, in the data in the system somewhere, and I'm happy. In the upper right is actually probably the most common, which is quorum. Ensure that a majority of the nodes are actually seeing the data. And then we can do a little bit of interesting things with respect to guaranteeing certain data consistency things. And then in the lower right, it's actually the most stringent. We say, hey, I need to make sure that every node has actually written the write that I just got. Now, the lower right one has actually got some challenges to it, because if any node is down, then that write won't succeed. And so we lose some of our availability, which is one of the things that we're trying to keep very high here, is the high availability. And so quorum becomes a really popular choice for really two main reasons. One of them is it's a good middle ground between consistency and availability. I'm likely to have at least a majority of my replicas up at a given time, and as a result, I have good availability, and then as a result, I get a couple of nodes actually getting the data. Now that's the write side of things. Now on the read side of things. So now we've got our client here on the left is doing this query. This looks like SQL. It's actually CQL. It's very similar in that intersection of space between them. And again, he's going to contact a coordinator. It could be anyone. And he's going to ask this question, give me the user ID for the user whose name is PB Cup fan. All right, so the coordinator says, no problem, let me go get that, and consults with some number of the replicas based on the consistency level. So let's say that he did it on quorum, and so the coordinator is asking two of the nodes for what they have, and they each give him the value that they've got. Now, they may be different, right? We said before, very active system, we said that you could end up with only needing to ensure that one or two or a subset of the nodes got the writes. So when you ask the question, you may get different answers. And the way we do that in Cassandra is that when we do the writes, we put a timestamp. So what the coordinator has to do in this case is he's not trying to see if the values are the same. This is not a majority votes, majority wins system. This is a last write wins system. So he's going to check the timestamps, and he's going to return back the value with the highest timestamp. So if we combined a quorum write with a quorum read, we can make sure that we always get the most up-to-date data, because we're going to be consulting one of the guys who got the previous set. Now, this is all interesting. This is a very basic how Cassandra is working, how we get a basic scale-out system. But the interesting part's really not about, especially with Internet of Things, the individual thermostat, but rather a whole stack of thermostats. And then, if we're going to be at all successful, this ramps up to many thermostats and then zillions. Okay, so that's sort of where the general concepts of Cassandra are. And Cassandra really is well suited to the Internet of Things for the space where we talk about always on, so there's no downtime. We're always going to be able to receive the data from the Internet, as well as be able to serve up to queries. We've got this scalability so that if we get successful, then we're able to scale without having to massively re-architect things, and that makes it a really good choice for Internet of Things. Okay, so now this is really positioned as being a place where the data is. But like I said, Cassandra alluded to, Cassandra doesn't do everything. It's great, it's awesome, we love it, but it does come short by design of doing certain things. So one of the things is that it does not do aggregates, and so it's really been optimized to do lookups and to do writes, but it's not really about doing large group by aggregates or even the more fancier windowed aggregates that you get in SQL. We also don't do joins. So much of that is where we spend some time with people who are new to Cassandra, because there's a data model change. And we can really cover most of the join use cases by intelligent use of data modeling, and so we can work around some of these problems. They're primarily lookups, like I mentioned, so we talk about needing a partition key, and sometimes the predicates aren't based on the partition key, and that's another challenge that we hit with Cassandra, and essentially Cassandra is not designed to be this full table scan kind of place. So we need to have something else helping us out here, all right? So we talked about the peanut butter. Let's talk about the chocolate. So Spark, distributed computing framework. It's been, let's say, it went GA, version 1.0 went GA last spring. It's got this generalized execution model. It can make reuse of data that it has already pre-calculated. People talk about Spark being an in-memory system. It's actually more than that. It actually does work off of disk, but I think the thing that's really important to keep in mind is that Spark is really good at reusing memory and very efficient there, and so that pays a lot of dividends for folks. And then there's this easy abstraction, this thing called data frames, and a whole bunch of other tools that are built on top of this. So if we look at the Spark ecosystem, or the Spark, product, it's got a number of elements that are all integrated here in one place. We've got a basic core, and then we've got a SQL engine, a streaming engine, and then there's a few other pieces that I won't talk as much around, machine learning, graph analytics, and R and statistics. So this is the general high-level view of the stack of Spark. Now, Spark is a relatively simple architecture to understand. There's only two roles of the nodes in the cluster. There is a master, which we've talked about a little bit before, and some workers. We've got this, like I mentioned, efficient memory caching and this generalized model, which is really nice, and this abstraction called data frames. Now, if I'd given this talk about 6 months ago, we would be talking about resilient distributed data sets, or RDDs. A lot of similar things can be said about them. Data frames are the sort of new re-envisioned version that actually gives a lot more capability, but conceptually speaking, they share a lot with the concept of an RDD. So the Spark master, he's the one who you submit jobs to, and he assigns resources to a particular job. The Spark worker is the one who now has tasks that he needs to do, and so he assigns work to the local executors running on this machine, and then the executor is actually the little bit of code that's doing the work. He's the guy who's taking a part of the data frame or the RDD and processing the work that comes out of that. So the RDDs or the data frames can be generated from a whole host of sources. We got things like HDFS and text files and databases and Apache Cassandra. All right. So now we'll talk about sort of how the two pieces fit together. So the way that Cassandra fits in with Spark is on the bottom, and so we can put a Cassandra source or a Cassandra database underneath the Spark core engine, and we've got this piece called the DataStax Spark Cassandra connector that is basically the interface code between the Cassandra database and the Spark engine. That's an open source technology or package that we've got out there. We contributed out. There's others who are contributing, but DataStax is doing the lion's share of that work. And what that does is it surfaces Cassandra tables up to the Spark engine as a data frame. And by integrating in at the bottom, by integrating in at that lower level, we're able to take all the elements above it, the SQL engine, the streaming engine, the machine learning engine, and we're able to just reap the benefits of that from this concept and this data structure of the data frame. If we dig in a little bit and take a look at what's really going on under the covers, I mentioned this Spark executor. So the Spark executor is the workhorse. He's doing the processing of the data that is sitting in the data set or the data frame. He's taking it piece by piece. He's working it through the DAG of execution and processing it. So the way that it is inside of that executor, we need to take a look at how he's grabbing data from Cassandra. So each one of those executors has a connection to the Cassandra database that he's making through the Java driver. So DataStax, another thing DataStax does is builds a whole bunch of the open source drivers for Cassandra. This one happens to use the Java driver, but there's a number of other drivers available. And he makes a connection to the cluster. Each of these executors will then pull across a part of the data frame or part of the full data set and bring it across. And so what we do is we split these up, RDDs and data frames each. They split up the full token range into pieces, and a Spark executor will operate on all of the data for a subset of the tokens. So just in this picture, the first slice might be tokens 1 to 1,000. The second one could be 1,001 to 2,000, et cetera. And we work our way through the entire data set that way. We can work in these in parallel. So conceptually speaking, we sort of have this situation where each Spark node, these orange nodes on the left, orange marbles on the left, are each making a connection to a sister Cassandra node on the right. This is a simplified version. There's really no reason why the Spark cluster and the Cassandra cluster have to be the same size. But for simplicity, we'll just display them this way. And so they buddy up. And so the top Spark node there might work with the top Cassandra node, and they're going to be reading the data that is owned in that space. Now, once you see this picture, you sort of rapidly come to, why are there two different clusters? Why don't we co-locate the Spark process and the Cassandra process on the same node and get these sort of hybrid nodes? We'll run the Cassandra and the Spark on the same thing. That allows for us to do local reads and writes, and we can skip some of the network costs of doing Spark here and save that. And so we end up with this sort of Spark Cassandra hybrid. So now that we've done that, let's take a look at things that we can do now with Spark that we couldn't do before with Cassandra. So the first one is join. So this is a silly little example where maybe I have some metadata about each of my sensors that is in this table called metadata, and I have another set of data that actually has the temperature readings. And I might want to know, say, tell me what the temperatures are for the last, that you have in the data set, but show me also the location for that sensor. And so this is a relatively simple join. They certainly can get more complicated than that. The second example we got is aggregates. And so now I might be interested in the year and monthly average, or I'm sorry, maximum temperature for each of my sensors. So this is actually going to do that kind of full table scan and grab the data and process it and give us this summary table, sort of an OLAP style query. Now, one of the other pieces in the Spark ecosystem, there's a lot of use of distributed file systems like HDFS, and they may be external to the cluster that we've got. Well, they're certainly external to Cassandra, which does not have an HDFS in it. And so we might want to do a join between the two. So we have our HDFS data is, say, the data of temperatures from 2014. Maybe they're stored in CSVs or something along those lines. And we'd like to join it with the data that we have, the hot data that we've got in Cassandra, the operational data. And maybe this is a query, this example is trying to say, in this first line, you define the HDFS data set. In the second line, we were defining the Cassandra data set. And in the third line here, we're joining the two together and then doing a little filter to find out which sensors are hotter this year in this month than last year in this month. So relatively simple, but I just wanted to give an example of sort of a year-over-year kind of query. And then the last example is super simple. This one's just saying, hey, what if I wanted to restrict my query based on not the partition key? In other words, I'd like to know every time there was a temperature reading above 100 degrees. And that's just over the entire data set. And again, Spark is well suited to scrub through all of that data. Because we're integrating in with Spark, we can latch into the entire Spark ecosystem of tools. One of the pieces there is through ODBC and JDBC, because Spark SQL has that interface. And so we can tap then into things like Tableau and Pentaho. And I put R here. There is a Spark R capability, but there is also our ODBC and our JDBC. And you could leverage those just for getting an extract of data. And then there's some notebook style tools like Apache Zeppelin, that's an incubating project in Apache that we could also tap into. So the Spark ecosystem enables a number of tools that are in addition to the tools that we've got in the Cassandra ecosystem. So I'll do a quick word on Spark Streaming. I'm conscious of the fact we got a late start here, so this will be relatively quick. Spark Streaming is one of the big things that we're seeing a lot of folks use with Cassandra. The idea here is that you've got a number of data coming in from the ether, and they're going to come into into a receiver. And so we could think of this as, again, we could do this with say, the sensor data, temperature data coming in from our sensor network, et cetera. And then what Spark Streaming does is it basically makes these little windows. And so these dark blue boxes are, say, 1 second windows, let's say, that we're going to build up. And so we end up making these little batches. It's really kind of a micro batch kind of approach. And so we build up all the data for 1 second, and then we can process that 1 second. Or some collection of them. And so in Spark Streaming, we can say, I'm going to put them in 1 second buckets, but I'm going to do, like, say, every 2 seconds, I'll do the actual processing, and I'll slide by 1 second. So that's what this example is at least illustrating. And maybe I'm doing rollups. I could do pre-aggregation. I could do some filtering. I've got anything I want to do here. And then I can take that data and persist it somewhere. And one of the things we see a lot of people doing is using something like a message queue, like RabbitMQ or Kafka, and then pushing it through Spark Streaming and then have the results go into Cassandra. I'll skip going into the details here, but there's some relatively basic commands that you would need to do to set this up, and it's relatively straightforward by setting up what the receiver is, setting up what you're going to do on each window, and then telling it to keep running until you decide to stop. Just a quick plug on DataStax Enterprise. One of the things that DataStax Enterprise delivers is Cassandra at its core, but we have these other capabilities. We've got this Spark integration built into that platform, as well as our integration with Apache Solr on the search side of things. So now if we come back to our Internet of Things use case, we can see where Spark and Cassandra where Cassandra fits is in this system of being able to receive all this data and scale for all the toasters we're going to add to our system, and how Spark really helps us address this broader set of questions that the person on the bottom is going to want to do with that data. And so if we kind of come back then to Willie Sutton, we really see that one of the real benefits here of getting Cassandra and Spark is being able to unleash the power of analytics where the data is. And that's really the big